Okay. So, is my screen visible? Can you confirm, Nakul?
Yeah, it's visible. I'm audible,
Yeah,
right? Yeah,
you are audible. Yeah.
yeah.
Okay. So you might be hearing some background noises. Please ignore that.
No, no, it's
Uh,
completely fine. It's completely fine.
yeah. Yeah. Okay. Thank you. So I'll briefly introduce myself so that you'll know my background, and if you're interested, we can connect on LinkedIn and we can discuss further. This won't be the traditional presentation or the lecture that you're going to see every time. So I just want to interact much and give you, the process. I strongly believe that process is important at this stage if you want to get into any new technology rather than traditional methods that people are following already. Okay, so myself, I am Dr. Avinash, and I did my PhD from Indian Space Research Organization. In fact, it is from Indian Institute of Space Science and Technology. I used to work in the research labs, one of the research labs that ISRO is having at Hyderabad. So I got fellowships at from the IIT Palakkad as well as AICTI in AE. So currently, I work as an associate professor at Department of Computer Science Engineering at Gayatri Vidya Bharshad. And I also work for industry through collaborations through college, and most of my students work as the team members of that company, and they are into development and all. So it's like learning while they are in the college itself, so that they can perform in the industry better at the later point of time. So that's briefly about me, and yeah. So this is very general discussion. So if you are interested in quantum computing or any quantum technology, linear algebra is a must. So that you might have already realized, but the importance of linear algebra, even if you start learning this machine learning, deep learning, all those concepts, even for this generative AI, linear algebra is must. And to do hands-on and to learn something, programming is the only way. So basic Python programming is important to learn quantum technologies and to try them on simulators, because most of the quantum software development is all the SDKs, almost all are being developed in Python. And the most important aspect is you should not have a kind of tendency to compare both quantum and classical computers, because those are not replacement for each other. They go hand in hand to solve some complex problems. And main thing is you should enjoy quantum mechanics, because no one can understand quantum mechanics. That's what told by all the quantum mechanical sciences. And most important aspect is you should identify the right problems. In fact, you cannot solve everything on quantum, so you should not try everything on quantum. That's very important. Also, I will touch upon the different websites and packages that we have to draw the quantum circuits and other available simulators. I'll walk you through different websites and all. I did not put all the content into this, just to make it very casual. And I'll also point out to some online resources so that you can go back and refer to them and you can learn. So after this, you will understand the hype versus reality. A lot of companies and a lot of industrialists or even researchers are giving hype about quantum computing, but not just quantum computing, any quantum technology. Then we should also understand the reality. And where we can use quantum computing, you'll get to know after this, partially, but there is a lot to explore. And you'll understand what is quantum machine learning and why quantum machine learning when we have well established machine learning techniques, products like ChatGPT, and how to experiment quantum machine learning. And if you're interested, I'll also point out how to write research outcome of your process that you are going to learn. Okay, so I'll give brief introduction, very quick introduction, because I planned the lecture, I mean, this talk till 4:30. So mostly I'll be giving very quick things, and if you want me to elaborate or if you want to discuss further, we can plan some other day or some, even we can discuss online. And quantum machine learning approach, I will also specify. Most importantly, quantum computing for data processing, all these things. And I'll also discuss the career opportunities, job opportunities, how to explore those and where to get and how to connect to people. So connecting to people is different from networking. Uh, Networking is important rather than just connecting to the people. I'll start with this data because quantum machine learning is about data. So you see lot of hype and lot of evolution of data and the rapid pace at which it is growing. All these things, it we will be having exponential growth in data. That's what the slide is meant to point at, and which leads to the evolution of big data analytics, where volume, velocity, variety, veracity, and value of the data are very important, and which are to be handled perfectly in order to get good insights out of it. So big data, basically, these are the 5 V's of big data, which describe, in fact, these 5 V's describes the big data properties. There are many applications which you are already using on your mobile phones. And this is the important slide. So traditional programming, you have program, you have data. So I'll use this. Okay, so you have data and you have program, and you execute data along with the program on some system and you get the output. But machine learning is a different way. So this is a very basic slide. So you have data and you already know the output, and you give this. You prepare a program so that your you build a model so that it learns from both data and output together, which is supervised learning. And then you ask a question on unseen data, and it gives you some predicted output. So the aim is to make this predicted output, which is very close to truth. So this is prediction, and there will be actual truth, and you make the machine learning model in such a way that it is very close to the truth. So that is what machine learning is. So it is development of computer programs. In fact, these models are computer programs that can access data and practice to learn themselves. Of course, model is a bunch of matrices. In fact, which involves a lot of weights and these things, but ultimately it is outcome of a computer program. So that is what traditional machine learning is. And sorry, and why are we worried now? So say if we consider supervised learning, so you will be having input machine learning algorithm, output, all that stuff. For classification, this is an example. But now you have data, you have model family, you have loss function, or you have some background in machine learning. If not, I'll briefly explain this. So data, you need to have both input and output with you, so that you can choose a model family in order to build a machine learning model out of this data. And your model looks like a mathematical function which is completely non-linear. Of course, linear mathematical functions can also be there depending on the problem that we are taking. And you will have input and trainable parameters, so that you will minimize the loss, which is also a mathematical function. So basically, this is the predicted one and this is the actual one. All the goal is to minimize, keep them as close as possible. So that is the goal of machine learning. Now, as the data increases, the dimensionality increases, the complexity of the data increases, the understanding ability of the machine learning model also becomes tricky. So dimensionality of data, class labels, imbalanced data, in fact, noisy data, inaccurate data, all these kind of properties creep into the data, and it questions the efficiency of the model, interpretability of the model, accuracy of the model, and also energy, because you need to execute for longer hours to train the models and also to get the output and all that stuff. So there will be huge increase in the training parameters. Model selection becomes difficult because simple models won't be sufficient in order to handle those, and you need very complex models. And then to execute these complex models, you need computationally efficient hardware. So normal hardware won't be sufficient even to execute a small, if you want to train a GPT-2 kind of model, you need to have at least 12 to 16 GB of graphical processing units capacity, VRAM. And then memory intensive algorithms also evolve. So that's the main problem. So then people started looking, as hardware is the primary focus in order to execute these machine learning models and all, and also to process the data. So people started looking at how to increase the computational power. So they started increasing the number of transistors on the chip, and slowly, they found that materials started to behave in quantum mechanical fashion when they are going to make those miniature sized transistors and all. So then, this is the second quantum revolution where many companies started manufacturing quantum processors with materials that behave in quantum mechanical way. So the traditional definition is quantum computing is a process of manipulating quantum mechanical information. The main aspects are superposition, entanglement, and interference. Believe me, if without understanding what superposition is, what entanglement is, and what interference is, you cannot get into any kind of quantum technology, whether it might be quantum computing, or it might be quantum memory, quantum QKD, or any quantum communication related or sensor related things. You should thoroughly understand what superposition, entanglement, and interference are. These are some of the basics related to quantum computing. I'll quickly walk you through this. So classical bit, so you will have both on and off the voltages. And then quantum bits are superposition of both 0 and 1 at the same time. And those can be represented using this. So these are subatomic particles. It might be superconducting qubit, or it might be a photonic based quantum processor, trapped ion, NV center diamonds. So we have around 8 to 9 prominently, built quantum bits. So you can consider them. So quantum computer works on quantum bits, and the basis states are get 0 and get 1. So get is a Dirac notation, and you can represent a qubit as a linear combination of basis states, both 0 and 1, at the same time with the probabilities and amplitudes. So this is why linear algebra is important in order to understand all these matrices behind all this particular scenario. So the state of qubit is indeterminate state. This is not due to any other traditional computational methods. It is the primary property of super qubit. So that is why people are able to achieve superposition. And only if you measure, you will be getting information out of the qubits. So you might be wondering, how is it possible? Because of the hardware. So that is why in second quantum revolution, people are able to experiment all the quantum mechanical properties, because of the development in material science. Till now, material science, which is related to quantum, is not that developed. So now, during second quantum revolution, there is huge investment and drastic development of all these stuff. Okay. Yeah. Some of the important differences between a classical computer and quantum computer. Here, computational power grows exponentially. That means if you have 2 qubits, I can represent in 2 square states. If you have 3 qubits, I have 2 cube states to represent. So that's why it's exponential growth. So, yeah. So qubits are manufactured using subatomic particles, whereas classical computers are made of CMOS circuits and other traditional stuff. Quantum computers, quantum processing units. In future, people are expecting that you will be having CPUs And as now you are using Google Colab and other cloud resources where you will have GPUs over that. Similar way, of course, we are already using the cloud resources with quantum processing units in that. I'll also point you to that particular thing, which is by IBM, which is very relevant for your program. Okay, so QPU quantum processing units solve only specific problems which are not the traditional ones. And if you want to do some general purposes tasks, it cannot be performed on quantum. I mean, it is waste of money and time in order to do that. So now, uh, the main aspect is classical computers won't exhibit property of entanglement. Qubits exhibit property of entanglement, which is very important in both computation as well as communication applications of quantum. Okay, so these are all some basic things that I plan to discuss, but hopefully you can find them. I'll point out to the different resources where you can find these. But the basic information processing unit of a quantum computer is qubit, and qubits are two-level systems, and qubits are three-level systems. Uh, and these can be represented in complex Hilbert space. So ket0 can be represented using this particular vector notation, and ket1 can be represented using this particular vector notation. So if you want to initially all the qubits on the quantum computing process are on ket0 state. So if you apply some unitary matrix on that, then only you'll be able to convert it to some other state where you can use this for computation, or even this can be your computation, and then your 0th state will turn to some other computational state, so that you can experiment on different things that you are planning to do. Okay, so there will be single qubit gates. So gate in the sense it's a simple unitary operation. So initially you'll be having basic get zero state, and then you will be having these unitary matrices, which are also the gates, and then you will have a different quantum state. This is very famous one, Hadamard state, where it pushes the qubit into equal superposition of both 0 and 1 at the same time. Only when we measure, you will find whether it is in 0 state or 1 state based on the probability. All that basic things are a little complex to explain in a short time. I'll point out to the resources. And not just single qubit gates, you will also have rotational gates where you can push the qubit into some intermediate state. Again, these are all matrix operations only. So whatever you do in quantum is linear algebra. And then you will also have two qubit gates where you can represent it. If you have two qubits in hand, you can represent the states in this fashion. So 0, 0, 0, 1, 1, 0, 1, 1. That's why two qubits will be represented using two square states. So you will have four states to represent if you have two qubits. And yeah, so this is one of the famous gates again, C0 gate, where you will have both control qubit as well as target qubit. And when the control qubit is in state 1, then the target qubit will be flipped. You observe? So this is the initial state. The control qubit is 1, and we apply this gate on both the qubits. Then the target qubit will be converted to 0. So this is control qubit and this is the target qubit. So if you observe, the control qubit is 1, the target qubit will be flipped. So this is the target qubit. So these are again the matrix operations involved. So this is the vector state of this particular state 1 1, and C0 gate can be represented using this matrix, And simple matrix operation gives you this particular state 1 0. So the state, yeah, 1 1 can be converted to 1 0. So that is the main idea. Why I'm explaining all this? So whenever you want to do some computational operation, so all the computation algorithms are represented or are designed in the way of quantum circuit. So only quantum circuits uh, will allow you to do computation. And quantum circuit is nothing but a combination of single qubit gates, multiple qubit gates, and along with some measurements. So if you don't have measurement, you will not be able to get the information out of it. So it will be in indeterminate state. So only when you measure, you will be having some classical value. So qubit measurement results to some classical value. So again, these are the operations where you actually measure a qubit. Measurement is nothing but again a linear operation, matrix operation in this particular form. Okay. So you have qubits, you have gates, and you have measurements. So this is the usual scenario that we need to follow in order to execute any computational algorithm. So similarly, you have qubits, you have gates, and you have the measurement operations. So this is a very famous circuit which supports superposition and entanglement, and which can be formed using just Hadamard gate and CNOT gate. So if you want to push two qubits into superposition and entangle them, so this is the circuit. So I'll share this PPT with Nakul so that you can refer to these things later. I'm skipping all this math because I'm pretty much confident that you can understand in a single read. Okay, so this is just a derivation to show that it pushes the two qubits into entanglement state. Okay, so then you will have 50-50 chance to obtain classical value 0 or 1 when it is measured. So depending on one qubit, the measurement of other qubit also changes. So now why are we looking at quantum machine learning? So machine learning algorithms are very efficient to handle the huge amounts of data, but the size of data, rapid pace at which now it is being generated, it is testing the ability of machine learning algorithms. Then you definitely require efficient hardware and very efficient and computationally intensive algorithms. So now people started looking at quantum computing as a rescue thing, which can help them to handle complex data, and because of superposition and entanglement, and also as I pointed out, that quantum computing is all linear algebra, and there are very powerful techniques in quantum computing related to linear algebra, which in fact machine learning is totally linear algebra. So people started relating these two with each other. Also, there are some challenges. At present, we have very less number of qubits. So now the primary aim is to solve machine learning problems on present day quantum processing units. Even though there are plans to get qubits increase the number of qubits, but noise is always a problem in this NISQ era. Hopefully, in maybe 5 to 10 years, that won't be the scenario. Okay, so now this, I feel this is very important for you all to understand. Uh, if you want to work in quantum machine learning, first try to master in machine learning. If you don't have strong background in machine learning, you'll not be able to understand where to apply quantum in that, because you cannot try every machine learning algorithm with quantum computing, which is a dangerous thing in fact to do, because it would consume a lot of resources as well as time. It is very important to understand the requirements and define the problem statement. If a simple mathematical equation can solve my problem, there's no point to execute that on a quantum computer. And yeah, so understanding requirement is very important so that you will define the problem statement very efficiently. I strongly believe that this is the process we need to keep in mind, because there might be many methods in doing, but process is important to you know invent or discover your own method of solving a problem. So data acquisition, you have ETL tools, SQL tools, and all. So after defining the problem statement, you should get right data. So if I don't have right data, even if I define the problem, I cannot solve it, because only if I analyze the right data, or if you try to find insights out of the right data, I will be able to solve the problem. And then of course, if you give garbage to a machine learning algorithm, it gives out garbage. So data preparation is very important. Then simply by plotting, I can solve some problems. Just data visualization gives solution to many problems. So that's why exploratory data analysis is very important. And then we will focus on modeling, evaluation, and interpretation. So imagine you are building a machine learning model, or you are building a deep learning model. So you will be able to do this. And then most important thing is you observe, you record the results, you deploy the models in the real time scenario, using ML ops or something. And then you will test the models in real time. Might be A/B testing or some other scenario for testing. You can do that. And then you retrain based on the outputs that you have recorded. You should handle the failures, process all the change the process, or process all this information again. So now mostly you should be able to improve the models, you should be able to collect more data, you should be able to find more features, because feature engineering is really crucial in any machine learning algorithm, and you should be able to optimize the code. So I have highlighted data preparation, modeling, evaluation, interpretation, and optimization to improve models in all these, because there is scope for quantum computing in these three steps. So when you prepare data, you can process it using quantum computer, so that you might get different numbers than you do classical processing. See, ultimately, for your model or for your program, it is all just numbers. Whatever the data you process, it is just numbers. Getting good numbers is important. That's what your convolution neural networks models do while recognizing any object or recognizing any people's face or something. So this step, you can try quantum computing. You can try, but there's no guarantee that it would be giving you good results. It's all about trying and failing better. And then modeling and evaluation again. So you should be able to process some information on quantum, some information on classical, maybe GPUs or some other computational devices, and then you should repeat this scenario. So that's why when you plan for modeling, you can plan that way, that you can subdivide the problems and you can use different scenarios. And then you can improve the models, you can get more data, more features, even through quantum processing. You can make an efficient circuit which is suitable to get image features out of it, all this stuff. Okay, so this is traditional machine learning project workflow. In this traditional machine learning project workflow, these are the steps. I believe this is not the industry standard or something. I personally experimented and I felt that okay, these are the steps where we can try quantum, so that to improvise machine learning. All idea is to improvise quantum machine learning using quantum. So this usually you see in Wikipedia, this slide. You will have data which is classical, then you do classical processing, you have data quantum processing. all this stuff. But right now we are focusing on classical data and quantum processing. This is the era where we are focusing on this particular, cell of the matrix. And yeah, this is almost my last slide. Then I'll shift to this thing. So you have big data processing, then you will be using data encoding, then you have some softwares like Pennylen, Qiskit, all such stuff in order to create quantum machine learning models. And then you do measurement and you do cross processing. I specifically highlighted quantum, TensorFlow, quantum, Pennylen because these people, of course, IBM, Qiskit, and I did not mention this IBM Qiskit because, in fact, these are aimed at computers which are here only. So that's the main issue with quantum computing, that you try experiments and do things. Okay, so you have data, you need to first encode it in order to process it on qubits, and then you build machine learning models, and then you measure them, get some information out of it. You can directly use it as a result, or you can post process it to get some results. So yeah, so these are the things. So if you have any questions, I can answer. Else, I will point out to some resources where. Uh, Give me a second. Yeah, sorry, I have to take an important call. So
Can you take a couple of questions?
sure, sure.
Uh, yeah. Shreyas here has a question.
So, could you please highlight a bit about the opportunities in quantum machine learning and quantum computing in general, the current state of the field using models,
Sure, I'll do that.
open models?
Yeah, thanks for the question. Okay, so
Sir, I think you mute yourself first.
oh, sorry. Yeah, thanks for the question. So I have opened few links for you, and you can browse through these in order to find different opportunities available. So if you look at these jobs, and by looking at this, don't get disappointed. Most of them will be postdoctoral positions, teaching positions, and all these things. But this is the harsh reality. You need to understand that people are paying for doing research and getting good technology ideas out of it. But you will have ample of opportunities because, believe me, most of the research is driven by interns, uh, young minds like you. So for that, you may not find out straight opportunity. See, if you look at this, you will have the summer internship opportunities. Okay, and sorry, yeah. So you'll have summer internship opportunities, and you should write to professors and it is all about networking. So you cannot find something which are straight for you, a fresher, or 1 or 2 years experienced, who can work on software development related to quantum or quantum QKD, all that stuff. You should explore the laboratories that are there in and around India, and whatever. See, it's very important to for you to decide on the vertical first, whether you want to work on quantum computing or quantum machine learning or something, and then you should be able to find out a particular vertical and then explore who are working in that particular vertical in order to get into those positions. But uh, opportunities will be for you as a freshers. You will have internship opportunities. Then you are good at work and all that stuff. They will keep you as project associates, and then they might you might be offered with a regular position, and also you can convert that position to a PhD and so on. So those are the usual ways, but you will try to connect with as many people as on LinkedIn, and you can try these hashtags, hash quantum, and follow these, because anything which is related to quantum will be definitely using they'll be posting on LinkedIn. Okay, so hope I answered your question.
Yeah, I think that was a great answer. I see there's a question in the chat box
Oh,
in the meet.
1 second, I'll
Yeah,
check
I
that.
can, yeah, I can. Could you talk a bit about the ways of data encoding?
Yes, yes. Data encoding, there are many ways, but traditional ways are not sufficient, like the traditional way of basis encoding, amplitude encoding, or rotational encoding. But a combination of all these can give you a good encoding technique. See, no single encoding technique can be suitable for all, because I love this question, because this is the basis for anything. So whatever you want to process on quantum, whether it might be image, text, or anything, you should be able to convert it to bunch of numbers, and these bunch of numbers should be very well managed on qubits. So that is what data encoding ultimately. So there are no specific ways, but people uh, encode it in different ways as per their requirement. You can see bunch of papers from MIT where they simply use rotational gates, repetitions, one after other, in a sequential way and parallel way, that way. So, in fact, you can come up with your own data encoding technique which is suitable for a specific application. So that makes a very good research and product application.
Yeah, thanks a lot, sir.
Yeah,
I hope Akshay had answered your question.
yeah.
Uh,
So yeah, I just wanted to point out to these two things. Qiskit test book you might have already used, and this quantum IBM quantum platform you might all have already used this. Uh, so try these things, and if you are interested in networking, try this Quantum Network Explorer. Actually, I have to catch a bus, so I was in a hurry. But I'll share all these links with Nakul so that
yeah,
you can get back. And some other textbook resources can be these things. Sorry. So quantum computing for computer scientists, which is you can learn basic mathematical stuff and all. This can be a good start. Quantum computing and applied approach. You will also have mathematical uh, insights related to quantum in that. And this book I love. If you want to start with quantum internet, this can be a very good start. Of course, if you are not a great fan of reading textbooks, this is the best start. This particular website, you can get all the information here. You can do hands on everything. You can browse some quick applications and all. And Quantum Open Source Foundation is where you can find different quantum software development kits. I'll share all these with Nakul so that you can pass it through who are interested in that. Okay, yeah, that's all from my side. Thanks for your patience. Thanks for the opportunity. It's always great to interact with young minds. So if you are interested, you can connect with me on LinkedIn with Avinash Chalumuri. You can type Avinash Chalumuri, and you can uh, see my picture. So we can connect. Yeah, the knuckle. That's all from my side.
Yeah, sir. Am I audible?
Yeah, yeah, now you are audible.
I lost connection. Sorry. Thanks a lot, sir. Could you please share these resources with me and
Definitely, definitely. I'll do it. I'll do it. That.
the slides also? That would be great.
Sure, sure. I'll send the slides as well as the resources and all the links in a mail to you. I have your mail ID.
Yeah, yeah. Thanks a lot, sir.
Thank you all.
It was a great talk. Thanks.
Thank you.
Thank you.